Now, right at the centre of all this, right at the very centre, is this great big ball of gas. You would fit 1,300,000 Earths inside of this thing. It's huge. It contains 99% of the whole mass of the solar system. Now you get everything together, the planets, the dwarf planets, the comets, the meteors, the asteroids, the dust, everything. You get all of that, and that's only 1% of the total mass of the solar system. This contains 99% of the solar system's mass. So it's a big deal. And because it's so massive, it has a very large gravitational field. It can hold everything in place. The reason the Earth goes around the Sun is because the Sun's attracting the Earth. You look out there at Neptune, billions and billions of kilometres out. You know, the Sun is still holding it in place, still holding it in its orbit. Go out beyond that into the Kuiper Belt, all these little Kuiper Belt objects being held in place by the Sun. Go out beyond that to the Oort cloud, where the Sun is nothing more than just a bright star. It's all being held together by the Sun's gravitational field. So it's a pretty amazing thing, really. The Sun itself is actually a big ball of gas. It doesn't have a solid surface, and it doesn't have a solid core. It is just simply a big ball of gas. And it's made up of hydrogen and helium mainly. There's other stuff in there as well, but something in the order of 75% oil of hydrogen, about 24% helium, and the rest is other stuff. And it's that which provides all the energy, all the life, everything for us on the Earth. If you think about it, every piece of energy that we can ever use, with the exception of atomic energy, every piece of energy we can use initially came from the Sun. Consider things like coal. Okay, it was originally forests. Okay, and you saw all the sunlight coming in, and it grew up and made big trees, and they fell over, and one thing or another happened, and it turned into coal. And when you burn that, you're unlocking that energy that was initially put in as the thing grew. So with a coal fire or petrol or anything like that, you're actually unlocking the initial energy that was put in there, and that came from the Sun originally. Here's a few statistics for you. The diameter, 1.4 million kilometres. Now that is really big, 1.4 million kilometres. It rotates on its axis. Just about everything does out there. It rotates on its axis. Now at the equator it takes 25 days to go around once. But the interesting thing is that because it's a ball of gas, it doesn't rotate in a solid lump. The equator moves faster than the poles do. Now, can you imagine what that would be like? The equator is going faster than the poles. Now, that produces a whole lot of interesting stuff. If you have a look at this, and we'll have a look at this soon. Okay, this is called differential rotation, and it causes a whole lot of interesting phenomena that happen on the surface of the Sun. We'll talk about that. The surface temperature is about 5,500 degrees Celsius. That's just on the surface. As you get deeper, it gets hotter and hotter, and in the middle, you're looking at hundreds of millions of degrees. And that is what makes some really interesting stuff happen. It's spectral type G2V. I bet you're glad I told you that. I wouldn't worry about it. It's just a classification they have. It means good stuff, you know. It's good to be a G2V star. And distance from the Earth, mean distance from the Earth, 149.6 million kilometres. 150 million kilometres near enough. So that gives you a bit of a rundown on the statistics of the Sun. Now, let's have a look at this differential rotation, because this is where I really wish I had a blackboard, but I don't. I should have asked Theo about that, shouldn't I? Okay, you've got this object, and it's rotating faster in the equator than it is in the top. Now, obviously, this is going to create some sort of stress. Now, the Sun's also got a very powerful magnetic field. The magnetic field actually goes out about 5-10 times the distance of Pluto from the Sun. So it's a big field. And because the Sun, this gas is very hot. Now remember I said earlier about it being, an atom being ionised, how electrons are stripped off or added to an atom. All this stuff is ionised. Now what happens is when you've got ionised gas, it responds to magnetic fields. And it has the effect of locking the magnetic field in. If the magnetic field travels through an ionised gas, like here, it'll get locked in. And if that gas is moving at different rates, if it's moving more quickly at the equator than it is at the poles, the magnetic field will get stretched because it's locked in. So where you had a nice magnetic field like that, going across there like that, it begins to get stretched and it kinks like that. It kinks a bit more. Now imagine an elastic band. You pull the elastic band, pull it tight, and you start twisting it with your hand. Now what happens? Does anyone know what happens there?
Shortens.
It shortens, yes. And what else? Yes, yes. You've been here before. Yes, that's right. It'll actually kink. You get kinks forming in it. Same thing happens to the Sun's magnetic field. When it's stretched by this differential rotation, it gets a kink. And instead of lying down in the gas of the Sun, it pops up from the surface, boing, like that. Now, this is really interesting, because when it does that, it'll pop up, and it'll go back down. And where it pops up through the surface, form these dark spots. Now, most of the spots are actually in pairs. It's not always completely obvious, but you can see it there. See that one there? One there, one there. That's a pair. That's a pair there. There's another pair there. What's happening there is that the magnetic field is popping up like that, curling around and going back down again. So wherever you've got the magnetic field coming up through the Sun or going down through the Sun, you get one of these dark spots. And these, of course, are called sunspots. Now these are all over the face of the Sun. They, if you've, you can have a look at it through a telescope, but if you ever look at the Sun through the telescope, make sure you've got proper eye protection, and I don't mean a pair of dark glasses. Get proper filters, which do cost a bit of money, but then they save your sight. Don't attempt ever to look at the Sun through a telescope or with binoculars unless you have proper filters in place. The best way to do it is go onto the internet. There are a number of sites there which are linked directly to satellites, which are looking at the Sun 24 hours a day, and they'll give you all different information. That's where this came from. This came from the Soho satellite, and which I think is being decommissioned now. But that would watch the Sun in all sorts of different wavelengths and see what's going on. So the sunspots also vary with an 11-year cycle. They will actually increase, reach a top, and then they'll fall away and reach a minimum again after 5.5 years, and then reach another maximum after another 11 years. So they have this 11-year sunspot cycle. Now it does tend to vary a bit. It can be a bit early sometimes, can be a bit late other times, but basically it's an 11-year cycle. During the peak of a cycle, when you've got a lot of sunspots like you've got here, you've got all sorts of activity on the Sun, magnetic fields coming and going. The Sun can give off a lot of radio interference and gas and all sorts of things. It can be really active at a sunspot maximum. One time I used so the Sun's very dynamic. During a period of low sunspot activity, things are much quieter, you don't have as much radio interference, and so on and so forth. With the coming solar maximum, which should happen in a few years from now, they're expecting a lot to go on, and one problem is that when you have a lot of solar activity, it can actually damage satellites. So satellites have to be hardened against that sort of thing. Particularly the communication satellites, which brings in all the football and everything from all over the world, you know, the really important stuff. They can get knocked out, and if that happens, you're talking about billions of dollars to replace it, and not only that, you're going to miss your footy, which is far more serious. So it's becoming very important for us to monitor the Sun, to know what's going on, to understand how it's going to affect us on the Earth. And now with all these big electricity grids and so on, a major solar flare has the capacity to shut down the electricity grids. So one day your power can just go off. So all these things are now becoming very obvious as this technology spreads over the world. You've got to keep an eye on the sun, and they use the term space weather. So you've got to know what your space weather's up to. Now here we are, here's a close-up photo of a sunspot. This is the place where the magnetic field is coming up out of the surface of the sun. And here around it, this looks magnetic, doesn't it? I mean, remember when you were at school you did the thing with the iron filings? You get the magnet and the thing on top of it. Looked a lot like that. Well, it is magnetic. You've got the magnetic field kinking here, coming up through there, and going down through there like that. The part in here is the magnetic field has the effect of cooling down the material. So the surface of the sun's around about 5,000 degrees Celsius. The interior of the sunspot's much cooler. It's only around about 4,000 degrees. Now it's 1,000 degrees cooler than what's around it, so it looks dark. But don't put your finger in it because it's still quite hot. So there's your sunspot. You can see they get quite complex. There's sunspots everywhere. There's magnetic fields running hither and yon. All sorts of things going on. Now here's a large flare. This actually is an explosion which happens on the surface of the sun, and it throws material up into the upper atmosphere of the sun. But because this material is ionised, it responds to magnetic fields. So you've got a sunspot here and one here. You've got the magnetic field kinking like that. And what happens is that as that flies up into the air, it follows the magnetic field line. And you can see it goes up here, around there like that. It hasn't quite all gotten back down yet. It hasn't all quite fallen the whole distance there. But you can see there, you can see that sort of makes the magnetic field lines visible. And look at the size of the Earth in comparison. The Earth wasn't actually there, it was just put in the picture. But it gives you some idea. So here we have these huge flares throwing up from the sun. Enough energy in those to keep you going, keep Australia's energy needs for tens of thousands of flares. This is a X-ray photo, I think it is. X-ray or ultraviolet. And you can see here the magnetic field line here. There's a flare there as the energy's being released. But you can see how the magnetic field goes up, curves around, and comes back down. There's another one there. Very spectacular photos there. The Earth, of course, will be about that size.